Hello everyone, in this video we will talk about semiconductor physics, specifically PN junction. Now PN junction is the foundation of modern semiconductor devices, from diodes and transistors to solar cells and sensors. Understanding how charge carriers behave at this simple interface is essential for anyone working in electronics, material science, or even device engineering. In this video, we'll take a closer look into how to simulate a basic PN junction and see if we can actually get the result that is close to the literature value or the common graphs that you see in our textbooks. So I won't go into much detail, but a PN junction is simply a boundary or interface formed when a piece of a p-type and a piece of n-type semiconductor are joined together. The P stands for positive, rich in holes, which are located where an electron is missing, and the N stands for negative, rich in free electrons. So in a very basic and easy term, let's think of it like two different kind of chocolate bars, right? In one you have peanuts embedded in it, and in the other you have nougat, that is, think of it like electron. And if you press them together at the central region, the taste will blend. The interface between the two flavor in which all the intersection happens. So this is like the depletion region where all the action happens. So I won't go into much of the theory, that will take a lot of time, but let's look at some basic diagram that will help us to just initiate what we'll do. So let's look at what happens to carrier concentration across a PN junction at equilibrium. The graph on the left shows the overlapping profile. On the left side we have the n-type region, right? And on the right we have the p-type region. In the middle we have the depletion layer where there is a recombination of electron and hole pairs. So the graph here, you can actually see the concentrations. So specifically in this particular graph, you can actually see the concentration of electrons and holes. So now this particular region is n-type, that's why you can see the concentration of electron is large, and there is some kind of recombination happening in this region. That is why you see the curve actually pulls down, and for hole it rises up. So in this side you have the p-type, that's why you have large number of holes. Now this behavior is actually fundamental to how the PN junction works. Now if you add a bias, so let's say you add a potential drop, now depending on the polarity of the potential drop, either the depletion region will shrink or it will get bigger, and there you have like a switching activity. So it will offer higher resistance to the flow of current or lower resistance. That is the basic foundation of how a semiconductor junction works, right? And here also we have the concentration or profile. Let's say you have n-type and p-type, and this is how the concentration profile actually looks. So in our simulation we will try to see if we can actually replicate this graph. So let's see how we can actually solve this model in COMSOL. So we are in COMSOL. At first we will just add a 2D component because we will be working on 2 dimension. So we'll click on add component and then add a 2D component. So at first what we'll do, we'll add the parameters before even creating the geometry. So in the description I will write here, right? So we will use this concentration for now. Now in the geometry we'll change it to micrometer because the physics happen in the micrometer or nanometer scale, and since this is just a verification kind of simulation, so we'll just create a rectangle and I'll make it slightly low in height, and then I'll just add a layer so that I have 2 sections. So I will make the layer up to 0.5 micrometer from the left. So now we have 2 blocks with a partition in between. Now before adding the material and stuff, let us add the physics. So you can search semiconductor because we'll be studying semiconductor physics of carrier concentration and depletion region. So the best physics to do that is the semiconductor module. So I can right click on add to component 1. If you don't see here, you can also search semiconductor and it should show up, right? So yeah, I will click on add material. So you can go to materials and click on add material. So either you can add a blank material, but I just want to see with a common material whether I'm getting the depletion region correct or not. So I'll just add silicon. This is the most common material because even in books you will see the example of silicon. Okay, so I have added silicon in both the domains. Now I'll just add the carrier concentrations in the semiconductor module. Okay, so basically when setting up the doping in a semiconductor simulation, COMSOL offers two main approaches: the analytic doping model and the geometric doping model. The analytic model allows you to define the doping profile using mathematical expression or function. This is useful when you want precise control over how the dopant concentration changes with position. For example, a step junction or a gradual diffusion profile. Whereas in geometric model, on the other hand, let you assign specific doping concentration directly to selected geometric region in your structure. This method is straightforward and efficient when you have a device like a well-defined region with uniform doping and so on. So choosing between this option depends on the level of detail and customization in your simulation. So for now, I'll just add analytic doping and I'll just add a constant number. So for p-type, I'll just copy. So I'll just copy this, and here I'll just paste, and I'll choose this particular domain. I'll duplicate this so that I have another doping model, and I'll clear this and then select the second domain, and here I'll choose the donor doping as n-type. So if you're unaware, here in the impurity you have these two options. When defining doping in semiconductor simulation, you'll typically choose between accepted doping and donor doping. Accepted doping, also known as p-type doping, means you are adding impurities like boron to the semiconductor that create holes or places where an electron is missing. These holes act as the majority charge carrier in the p-type region. On the other hand, donor doping or n-type doping involves adding impurities such as phosphorus, which contributes extra electron to the material. This electron become the majority carrier in the n-type region. By specifying the impurity type for each region, you control whether that part of the device will have mostly electron or mostly holes as the primary carrier, which is fundamental when you are studying p-n junction or similar devices. So now that we have added the physics and the material, let us add a study. Now in semiconductor physics, there are different types of study. One of the unique one is the semiconductor equilibrium. Now the semiconductor equilibrium study in COMSOL is used to study the behavior of semiconductor devices under zero applied bias, meaning that the device is not externally powered. This study type focuses on computing the built-in electric field, potential profile, and carrier distribution that naturally forms due to the doping level on each side of a junction, like in the p-n junction we are trying to study. So I'll just add this study. Now in equilibrium, the simulation solves a coupled set of equation, including the drift diffusion model and Poisson's equation you may have read in semiconductor physics books. So this analysis is essential for understanding the device internal electric structure before any external voltages are applied. And this is quite important, I think, because if you are working with semiconductor model, you may have encountered when you try to add thin layer structure, you see that suddenly you have error and your solution is not converging. So many a time you may require to do the study step. Okay, so yeah, now that we have added this, let us click on compute and see what results we get. So we'll click on compute, and since this is a quick simulation, it should not take a moment. So yeah, so I actually made a small mistake. So I made the doping model both as p-type. That is why I'm getting poor result, right? So this will be n type, so I'll just make this n, yeah, and this will be n type. Okay, yeah, so now I have p type and n type, so I'll just copy this and I'll paste this. Yeah, so I'll run the simulation again, and hopefully this time I'll have decent result. Okay, so right now I have the electron concentration. This is consistent, it seems, because if I click on the doping, so I have this part of the semiconductor as p-type and this region as n-type. So if we look at the electron concentration, this particular region have less electron concentration compared to the right side. Similarly for hole, it will be the opposite. And then we have this electric potential profile. Now don't worry about this -5 to 4.3. You can think the extreme limits. So if you subtract, you'll see that the difference is around 0.7 volt, right? That is what we generally expect for silicon. So the built-in potential in a p-n junction arises from the difference in Fermi level between the n-type and the p-type region, which you can calculate analytically via some equation, and you can actually calculate it for some known material that are generally there in examples in some textbooks also. So this is the profile. Now let us try to actually plot the graphs that we discussed in the initial part of the video. So at first, let me add a 1D plot group. To do that, I'll go to results, click on 1D plot group, and then in the 1D plot group, so we will add a line graph, and then we'll select all the boundaries and define a cut line, because we are interested to see the profile along the x-axis. So we'll select a point somewhere here. It may not be very precise, it's fine, and another point here. And in the expression, I will paste the expression of the n-type concentration and the p-type concentration, and I'm just interested in the absolute value. So I'll click on plot, and you can actually see that this is the same graph that we have seen in the book snippet of the depletion region, and you can see that the 0.5 was the depletion, the junction, and since the concentration was slightly different on n and p side, that's why we're getting it asymmetric in nature, right? So this is the graph, and if we even try to plot it in a 2D plot, so maybe here we can just try to replace the expression. We can also see it visually how it looks. So you can see that the value is low in this particular region, and then it is slightly larger in this. So now that this part of the plot is done, let us actually try to plot the other graph, that is the electron and hole concentration separately. So what I will do, I will just cut this and I'll just plot the electron concentration, and I will duplicate this graph, and in this graph I will plot the hole concentration, right? And then if I click on plot, well, you will think that something is not okay since we are plotting both the electron and hole concentration. You have to keep in mind that since these values are in very high order, generally in books and everywhere people plot in the logarithmic scale. So we'll click on the logarithmic scale, and you will see this is exactly the plot that is there in the book, thus verifying the solution for the analytic equations for semiconductor physics for p-n junction. So in any semiconductor physics book, if you just open the p-n junction chapter, you will definitely see this kind of a plot for p-n junction, as well as the rising curve for the potential, right? So I hope this helps if you are just starting out with semiconductor physics module, and definitely try it using simple structure like p-n junction, etc. Then slowly try to add potential drop and so on. Hopefully this video helps. If it did, please do comment your thoughts. If you like the video, give a like, and thank you for watching. Have a nice day.